So with this video, we're picking it up with Chapter 7. 7 is titled Rational Numbers and Rational Functions. And so Chapter 7 starts out with a definition, and we're going to talk about rational as in numbers first, and then we're going to talk about, after we learn a little bit or refresh our memories of what it means to be rational for a number, we're going to talk about rational in terms of functions, polynomials, that sort of thing. So our definition is a rational number is any number that can be written pretty much as a fraction, with a and b being integers. Okay, so we want whole numbers, and those numbers could have plus or minus signs, basically. But we can't use decimal numbers or anything like that. So any number that can't be written that way is irrational. So we'll go down here and we'll look at example 1, and we'll pick out some rational and irrational numbers. Alright, now negative 17. It's an integer. 17 itself without the minus is a whole number. There's no 0.123 or any digits beyond this decimal point here. Now we just mentioned that a rational number is any number that can be written as a fraction with integer numerator and denominator. Negative 17 can be written that way. We can write it as a negative 17 and put a 1 in the denominator. Okay, 3.14. This number can be written as a fraction. Alright, we simply write 3 as the whole part, and then we take 14, and the 1 is in the tenths place, 4 is in the hundredths place. So what we're looking at there to the right of the decimal point is 14 hundredths. Okay, and to work this 3 into the fraction, we can simply say 3 times 100 plus 14, 314 over 100. So 3.14, any terminating decimal can be written in the form of a fraction with an integer on the top and the bottom. Okay, 2 3/5 is rational. The 2 can be worked into the fraction, and we do that by just simply multiplying the whole part by the denominator and adding the numerator. So 2 times 5 is 10, plus 3 is 13, and then we keep the original denominator 5 from the fractional part, and 2 3/5 written as a fraction, 13 over 5. So all of these numbers on the left are rational. Now with the square root of 2, we're going to bring up our calculator over to the side, and we're going to calculate square root of 2, and just take a look at what the calculator gives us. Enter. Now the square root of 2, if you'll look at it, looks like it terminates. The calculator can't give you all of the digits that appear to the right of the decimal point. We have 1.414213562, and they actually keep going. Those digits never stop. And another comment that you could make about them is they also do not have a pattern. It's not a repeating decimal. So a decimal number that doesn't repeat or doesn't terminate is irrational. And a quick rule for the square root is if the number inside, for instance, if we had the square root of 4, if the number inside is not a perfect square number, then you're going to get an irrational number. So in the case of the square root of 4, well, 4 is the perfect square, and we get 2. And 2 itself is obviously a rational number. 2 over 1 can be written as a fraction. But that's because 4 was a perfect square. 2, on the other hand, is not a perfect square. So we get this 1.41421. We get this decimal number that doesn't terminate or repeat. Okay. What about the other two? We'll find our pi, second, and the little exponential symbol here, the rooftop, and we can hit enter. And this is another irrational number. Okay, these digits never terminate and they never repeat. They never start to form a pattern at any point. Okay, so pi, irrational, square root of 2, irrational. We could write out some other examples using the square root of some irrational numbers. For instance, 3 is not a perfect square, so we could say the square root of 3. 7 is not a perfect square. Square root of 7 would be irrational as well. Which brings us to our last example here. And it goes along with what I said at the top. 16 is a perfect square. So if we take the square root of it, then we get an integer. Square root of 16 is 4. Okay, so this one is actually rational. These two, irrational. Okay, so one we can write as a fraction, the other one we can't, and a number is either one or the other. A number can't be both irrational and rational. Alright. Example 2 is simply touching on something that I said about decimal numbers. And there is a difference. They look like the same number, except they're not, because one has a bar over the top of the 3. This one is a terminating decimal. 0.3, and there are no more digits over to the right. This one, on the other hand, the bar symbolizes the fact that the 3 can be written to infinity. The 3 repeats indefinitely. And another way we could show that is to put a dot 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 here if we wanted to. But this is what's referred to as a repeating decimal. Okay. So there is a difference. Those numbers are not equal. So page 77, we have a definition here that is going to shed some light on some unique situations that you run into with fractions, okay, rational numbers. It says A is divisible by B, or equivalently B divides A, if and only if there exists a unique integer C such that A equals B times C. Alright. Another way that this can be thought of is if you look here, we can write A, if A is divisible by B, then we get C. Okay, why is that? Well, we can just simply use the fact that multiplication is the opposite operation of division, and we simply just say, well, B divides A and we get C, because if we take B and multiply it times C, we get A. Okay, and I realize that that may still not make a whole lot of sense. So let's look at a situation where we have actual numbers. 6 divided by 2. 6 divided by 2 equals 3. Why? Well, that is because 2 times 3 equals 6. Okay, reverse operations. And this seems kind of trivial, but it's actually going to help us explain the results of these 3 situations at the bottom of the page. Alright, so one way to think of this one, and this is the tricky situation I talked about, when we start involving 0 in division. Now you probably already know this one and have seen it before. 0 divided by 6, what does that equal? Well, it equals 0. Okay, how many times can you fit a 6 inside of 0? Well, that would be 0 times. But now we're going to look at it in terms of multiplication. 0 divided by 6 is 0 because 6 times this 0, the result, equals the numerator, 0. Okay, so in other words, this is asking the question, what number here, and that's to say if we didn't know what number that was, we just put a question mark there, and then we went over here and we took out that 0 and put a question mark. What number do we multiply by 6 and get 0? What number is that? Okay, that answers this same question here. What is 0 divided by 6? Well, the only number that will take this 6, multiply it, and give you a 0 is, of course, the 0 itself. 6 times 0 equals 0. So that's the logic that we're using here. Now example 5, different situation. We now have the 0 on the bottom. And you're probably thinking 0, but that's not true. So then you start thinking about, well, what number could it be if it's not 0? We go over to the right and we say, if we take 0, the numerator, just like we took the 6 and wrote it first, and we multiply it by this result, some number, and when we multiply those two together, we want to get the numerator, the 6. Okay, if we can find this number, then we know the answer to 6 divided by 0. Well, the unfortunate thing about this is no number exists. You can pick any number that you want to, and you can try as many as you want for as long as you want, and you'll never get 6 out of this because of the 0 product property. You could put 0 in here, but 0 times 0 is 0. You could put 6 in there. Okay, 6 matches the number over here that we want, but when you multiply it by 0, you still get 0. Okay, so what we say about this number, and likewise 6 divided by 0, we say that that number is undefined. It doesn't exist. So the point of that last page was that when you're dealing with fractions, or i.e. rational numbers, you do not want to divide by 0. And so that's what we're going to avoid when we're talking about rational functions. So on the next page, page 78, we define a couple things in the beginning: polynomial and rational function. So we've been using this word polynomial for a while now. It says it's a term or the sum of terms, and the exponents, and this is the one condition, I guess you could say, the important one. The exponents of the variables have to be whole numbers. We can't have negative exponents. We can't have an exponent of 1/2. Those aren't whole numbers. We need numbers like 0, 1, 2, 3, 4, 5, and so on. Okay. And one thing that may throw you off, but you need to get used to the idea right away, is that this is a polynomial. And a lot of times you think of poly as many, but this is only one term here. It's a single number, but you can still call it a polynomial. Alright? Now this one doesn't come as a surprise. You know, we've got letters and numbers mixed in. But one thing that you want to check, even if you have variables and numbers and a certain number of terms, you want to go and check off on the exponents of the variables. 3 and 2 are whole numbers. So this is a polynomial. Likewise, x and 2x minus 4 are polynomials as well. Now, our next definition, rational function. Well, this is what we call a function when we've taken one polynomial and then we've divided by another one. Okay, p of x is a polynomial, q of x is a polynomial. We take the two polynomials and we divide. This is what a rational function is. Okay, real simple definition. But the catch is, and don't just glance over something that has a large fraction bar and automatically think it is a rational function. Has to be a polynomial on the top and the bottom. Therefore, we have to check and make sure that it has whole number exponents on the variables. Alright, that leads us to example 6, and we need to pick out which one of these is a rational function. This one is a rational function. X is raised to the second power and 2 is a whole number, and then we just have a single number here, minus 1. So we can have the sum or the difference of any number of terms, and the exponents have to be whole. So this is a polynomial. You may be saying, well, it doesn't have a denominator. Well, just like we said, for instance, 5, or more specifically, one that we actually saw in the workbook, earlier we said that negative 17 is a rational number. And it was because we could take negative 17 and simply put a 1 in the place of the denominator. And there we have written negative 17 as a fraction. Likewise, we could write x squared minus 1 on the top of a fraction bar and just simply put a 1 underneath it. It's still the same function, we've just written it more like a fraction. And 1 is a polynomial just as much as x squared minus 1 is a polynomial. So we have a polynomial divided by another polynomial, and that is the definition of a rational function. Alright, now with this one, we see it's in fraction form. There's something in the numerator and the denominator, so it looks like a fraction. But now all we have to do is go and check off on the exponents. 2 is a whole number. When an exponent isn't written, it's understood to be 1, so this one has a whole number exponent. Likewise, the x on the bottom has a 1, that's a whole number. And then we're just left with 4 and negative 5. And those are polynomials too. So we have a polynomial on the top, polynomial on the bottom, and that does fit the description of a rational function. So this middle one's rational. And I'm going to have to erase some of this. This first one was rational. Alright, one other note, we don't see an x variable beside the 4 and the 5, but we could easily write one, x to the 0. Okay, and that's simply because anything raised to the 0 power, including a variable, is simply just 1. So putting an x to the 0 out to the side, well, it allows us to see a variable there. And then 0 is a whole number. But then putting x to the 0 there is just the same as placing a 1 beside the number. And 1 times any number is just that particular number. What about this last one? Well, looks like a rational function. We've got a numerator and denominator. We've got an x. We've got some numbers here. But this number here, square root of 2, is not whole. Not a whole number exponent. So this function, just this one little part, nothing's wrong with the x plus 3, it's a polynomial, but this square root of 2 rules this out on the top as far as being a polynomial. So as a whole, this is not a rational function. Not rational. Now, just like the functions that we talked about earlier back in chapter 1, a lot of times we're interested in figuring out what the domain of functions are. And there's a lot of explanation here, but the gist of it is with a rational function or any fraction, we do not want the denominator to equal 0. And so what that leads us to do is pluck out the denominator, x squared minus x minus 6, and we set it sort of equal to 0. So there's two ways you can think of it. We figure we could set it equal to 0, or we could use a not equal to sign because we actually don't want it to be 0. Okay, but that is going to be our MO for finding the domain. What we're really doing is we're figuring out what's not in the domain. So we figure out what makes this denominator 0, and then we say those numbers cannot be in the domain. So no other or better way to explain it to you than to actually work out an example. Okay, I'm simply going to take, and it tells us we have rational functions down here, and if you look at it and check it real quick, you don't see any non-whole number exponents. But we're interested in what's not in the domain, and then we can answer the question what numbers are in the domain. So automatically we pull out the denominator, and I always put equals to 0. I want to find out what makes this denominator equal to 0. If you want to, you can put a slash through it just like the workbook does. Either way, the numbers that we get from solving this equation are not in the domain. Alright, so we solved these in chapter 6, quadratic equation. We have to factor this trinomial, and we write x times x, and beside the x's we write minus 9 and a plus 1. Negative 9 times 1 is a negative 9. Negative 9 plus 1, we add them, gives us the b. So this is how we factor this trinomial here. And now we say x minus 9 could equal 0, or x plus 1 equals 0. If we solve these, we simply get x equals 9, and x equals -1. These and I'm just simply going to say here, these numbers are not in the domain. Okay, so that's all it wanted us to do. We'll go down here to example 8 and we'll do the same thing. If you look, it checks out. X minus 4 is a polynomial, x squared plus 25 is a polynomial, and all you have to do to check that is to look at the exponents. This is a 2, it's a whole number. This is understood to be a 1, it's a whole number. And -4 and 25 are just numbers, so they work. We do what we did in the last example, and we take x squared plus 25, and we'll set it equal to 0. Now, we have a quadratic equation, but if you look closely at this and you're careful, you'll notice that yes, x squared is a square, 25 is a perfect square, but in the middle we have an addition sign. We can't factor this. There is no solution such that we put a number in for x, square it, add the 25, and it equals 0. And you may be thinking, well, what about 5 and -5? Well, if we try 5, 5 squared is a positive 25, and then if we add 25 to it, we do not get 0, we get 50. Well, what about -5? Well, if we square -5, we also get a positive 25. And again, 25 plus 25 does not equal 0. So these were the only possible numbers where we could at least match the 25, and it doesn't cancel out the 25. So there is no solution to this equation in terms of a real value, a real number for x. And so off to the side, and again, first thing you should have picked up on is that this isn't factorable. Okay, but what we say at this point is there is no real solution. So this doesn't rule out any numbers for our domain. It turns out that the domain of h of x is, if we write domain, it is all real numbers. Alright, our function k. Here is our denominator. We do not want this denominator to end up being 0. So what we do is we set up an equation and we figure out what x's, what numbers in the place of x make it 0. Here's our equation. This one, we can take out a greatest common factor. We want to factor it at this point. It's in standard form, I guess you could say. 2 divides all 3 of these coefficients, and then each of the terms has at least an x. So greatest common factor is a 2x. X to the third divided by x, x squared. 6 divided by 2 is 3. X squared divided by x is a single x. -20 divided by 2 is a -10. And then x divided by x, the x's just simply cancel out. So we have one factor here, we'll keep up with it. And now we need to factor this trinomial. And we find two numbers that multiply to give us -10, and they also add to give us a +3. Those two numbers are +5 and -2. Alright, to figure out our x values, we set each factor equal to 0 separately. Alright, if we solve this little simple equation here, we get x equals 0. This one, we get x equals -5, and this one, we get x equals 2. These three numbers are not in the domain. So to answer the question, if we were asked what is the domain, we could write domain is -infinity up until we get to -5, and then we have to skip it. From -5 to 0, those numbers are included, but then we have to skip 0 itself. Then we pick it up with 2, okay, or we pick it up after 0 and we go out to 2. We include all the numbers between 0 and 2 except 2 itself, so we skip 2, and this is what that looks like in interval notation. So the interval notation of the domain, when you skip a lot of numbers, actually starts to get sort of long and drawn out. So I'll make a little bit of room here so things don't get cluttered. Beyond 2, there are no other numbers that are excluded from our domain, so we simply put infinity to end our interval notation. So what we've done here is we've solved the equation domain equals 0, and we are excluding these three numbers we found. -5, 0, and 2. And this is what that looks like. Okay, example 10 says write a rational function whose domain is all real numbers except -3 and 7. Okay, so what we have is some mystery function. I'll call it f of x. And it doesn't really matter what the numerator is. We could just put a 1 like we had with k. But now it does matter what we put down here for the denominator. Alright, now the denominator is what's on the bottom, and it's also what we've been taking and constructing our equation with. So we have this function. If we knew what it was, we'd simply say, well, take the denominator and set it equal to not 7, I don't know where 7 came from, set it equal to 0. Okay, and once we did that, we would solve the equation. And what they're telling us is that when we do that, we want to get a -3 and a 7, because anything we get out of this equation is excluded from the domain. And in the end, what that's going to look like is x equals -3 and x equals 7. So this is one of these problems where we have to work our way backwards. Okay? What factors of this particular equation, and ultimately our denominator, what factors would give us the answers -3 and 7? Well, that is x plus 3. Okay, and this x equals -3 would have come from this simple equation here, x plus 3 equals 0. And x equals 7 would have come from this equation, x minus 7 equals 0. And so these are the factors of our denominator. So to figure out our denominator, all we really have to do is multiply these two together. And originally they were set equal to 0 so that we could find these answers, these numbers that were excluded from the domain. So this is what we were looking for. This is our domain. So if we wanted to, we could just stop there and say, well, this is the factored form of our domain. But let's say, for instance, you were doing a multiple choice problem, and you looked in the multiple choice and you didn't see x plus 3 times x minus 7. Well, alternatively, you could see x squared minus 4x minus 21. You could go ahead and multiply them together, and hopefully this one would be in the answers. So either one of these. This is the denominator that excludes negative 3 and 7. And so this was a short chapter. That's the end of chapter 7. Thanks for watching.